back with the afternoon session, and we have Zhongshan An, who will be speaking on local existence and uniqueness of static vacuum extensions of Bartnik boundary data.
Hi, good afternoon, everyone. So it's my great pleasure to participate in this very nice workshop. Today I will discuss this static vacuum extensions of Bartnik data. It's based on a series of joint works with Lan, who is also here. Okay, so let me first introduce to you about the static vacuum pairs. So here we think of M as a smooth n-dimensional manifold, and we take a pair consisting of a Riemannian metric G and a non-trivial, non-zero function U on M. And this pair is called static vacuum if the pair satisfies those two equations here. And you see here, this is Laplace U equals to 0, Laplace with respect to the metric G. So this term in the first equation can actually be removed. But I keep it here just because that this equation is important in the study of scalar curvature. So we know we have this fact, which says that if a Riemannian manifold admits a non-trivial solution to the first equation here, then the scalar curvature map is singular at the metric G. And this is essentially because if we think about this map, which maps a metric G to the scalar curvature, and we take linearization of that map, then the L2 formal adjoint of the linearized map is just mapping the scalar function U to this expression here. Okay, so together with Laplace U equals to 0, we will know that the scalar curvature of the metric G must be 0. Okay, so we also sometimes we also call this G as a Riemannian static metric, and this function U is called the static potential of the metric. So this pair of static vacuum pair is also important in the study of mass in general relativity. It's proved in this work of Anderson-Jarrigge that if we consider the space, this should be scalar 0. So if we consider the space of all scalar curvature 0, asymptotically flat matrix with fixed geometric boundary conditions, then the Riemannian static metrics are actually critical points of the ADM mass. Okay, and in GR, it's well known that if we have this static vacuum pair, GU, then we can actually formulate a static vacuum spacetime here. And the well-known static vacuum spacetimes are the Minkowski spacetime and the Schwarzschild spacetimes. Okay, here in Minkowski, this G is just the flat Euclidean metric. U is potential function U is the constant 1. Schwarzschild metric G is this part, and potential function is square root of this part. Okay, so that's about static vacuum pairs. Yeah, so we consider the space of all manifolds with boundary, with a compact boundary, and on that compact boundary we fix geometric boundary condition. Actually, those are fixed Bartnik boundary conditions, which we will talk about later. Okay, so yeah, so today we would like to discuss this boundary value problem for asymptotically flat static vacuum pairs, which is to consider this system. GU should be asymptotically flat. G goes to flat metric, U goes to the constant function 1 at infinity. So this should satisfy this equation. Those are just the static vacuum equations on the manifold M, and this should satisfy those boundary conditions on the boundary of M. Okay, so here for simplicity, you can just think of M, for example, as Rn minus a ball. And then this boundary is like the sphere boundary. Okay, so those two is just we prescribe the induced metric on the boundary and prescribe the mean curvature on the boundary to be tau and phi. Okay, so those are called the Bartnik boundary data of this static vacuum pair. Okay, so this is like we want to know, does there exist solution for this boundary value problem if we are given some prescribed tau and phi? Okay, so here we have this very famous conjecture from Bartnik. It is conjecture that if we take omega G naught, which is a compact Riemannian manifold with non-negative scalar curvature, then if we take suppose the mean curvature is positive somewhere, so it's not degenerate, then there exists a unique asymptotically flat static vacuum extension for the data induced from this G naught here. Okay, in other words, it's just saying that if we take this tau and phi to be the Bartnik data induced from this filling in, then there exists a solution, exists a unique solution to this boundary value problem. Okay, so a solution to this is also called an static vacuum extension for the prescribed boundary data here. Okay, so this problem and this conjecture raises from the Bartnik quasi-local mass program. It is introduced by Anna Chiala yesterday, and yeah, so it's just saying that if we want to measure the mass of a compact manifold, then we will just take all possible asymptotically flat extension of that and take the infimum of those mass from those extensions. And it's conjectured by Bartnik that the infimum mass should be realized by a static vacuum extension. So that's why we want to study whether there exists such a static vacuum extension. Yes? Yeah, yes. It's let me see. They actually prove U is asymptotic. Like if there is a critical point, then the U must be asymptotic to 1. Yeah, they prove this fact. Yeah. Okay. Okay, so here are some so far some existence results for the static vacuum pairs in literature. So Miao and Anderson, they prove that we have local existence and uniqueness in dimension 3, and for prescribed data tau and phi, which are near the Bartnik data on the standard sphere in R3. So we think of sphere in R3, take the induced sphere metric, and the mean curvature is 2. If tau phi is near that, then we can have existence of static vacuum extensions, which is near flat. Okay, and it's locally unique. Okay, in dimension 3, and then Sadbaum, Rainey, Strela, they propose a flow approach to solve the static vacuum extensions for asymmetric boundary data. Okay, and actually, Anderson Jerry gave the conjecture counterexample. The conjecture that if we have a surface like this, which is which is immersed in R3 but not embedded, so like here it touches itself somewhere, then they conjecture that there is not a static vacuum extension for those boundary data induced on this surface. Okay, so that's the conjecture counterexample, and we also have a uniqueness result from Poning Chen and Xiangwei Zhang. They prove that if we have two surfaces both embedded in Schwarzschild manifold, and they have the same induced metric, the same mean curvature, then those two must be the same embedding. Okay, so in other words, they show that if we are given a prescribed tau phi here, and if we find Schwarzschild extension for tau phi, then that extension must be unique. Okay, so that's the uniqueness result. Okay, so besides those, I just like to mention that in literature there are many works about this existence of static vacuum extension or more general stationary vacuum extensions with different choices of boundary conditions. Okay, here those two works, and also if we impose two strong boundary conditions like here, if we require the boundary to be a minimal surface, then the only extension is Schwarzschild. Okay, and lastly, if there's no boundary condition, if we know the space-time or the manifold is complete in 4 dimension, then that stationary vacuum or like stationary vacuum is a more general concept than static vacuum. But that space-time must be flat if there is no boundary. Okay. So those are the all known work so far. And today I would like to discuss the existence of this boundary value problem nearby background solution. Okay, so let me first show you the basic framework of that local problem. So here we consider a general asymptotic flat static vacuum triple M is a manifold, dimension n manifold, and G bar U bar is a static vacuum pair on M. We recall that this U bar is non-zero. It's positive everywhere. Okay, and then we can just take arbitrary open bounded subset, do the minus, or if M itself has a boundary, and on that boundary U bar is positive, we can just make this omega to be empty. Okay, so we just want to construct a manifold with boundary. We call that boundary as sigma. Okay, and then on this manifold with boundary, we consider this boundary value problem, which is mapping a pair. This is arbitrary, any pair of metric G and scalar function U. It maps this map S maps this pair to those equations. So you see the first 2 equations are static vacuum equations. Last 2 are just the Bartnik data of the metric. Okay, so if GU is such that this is 0, the second 0, and this is the induced metric, mean curvature is equal to some prescribed data, then this GU is called static vacuum extension of that data. Okay, so we will consider this boundary value problem. We will study local behavior, so we will linearize this map at a background. This is a pair at the background static vacuum pair. Okay, you can take arbitrary background static vacuum pair G bar U bar, do the linearization here. Okay, so first 2 are just the linearization of those 2 expressions. We need to do both linearization with respect to H and linearization with respect to V. And the last 2 is just the linearization of the Bartnik data. So here is the induced tensor from H on the boundary. Here is the linearization of the mean curvature on the boundary. Okay, so it is proved by Anderson and Curry that if we use the correct gauge, which is called harmonic gauge, then this linearized operator is actually an elliptic boundary value problem, and the index is 0. Okay, so now like we would say if the kernel of this linearized problem is 0, then index 0 means co-kernel is 0, then this linearization would be a isomorphism. Therefore, we can use implicit function theorem to conclude that S is locally a isomorphism. But that's not true. In fact, we can just, based on a simple observation, we can say that the kernel of this linearized operator is always non-zero. So because static vacuum is diffeomorphism invariant, if we have static vacuum pair, we can just act on it by any diffeomorphism. Pull it back, we get another static vacuum pair. So those diffeomorphisms, those kernel elements generated by those diffeomorphisms, which are those here, for any vector field, we can just take the Lie derivative of the metric with respect to the vector field, take a Lie derivative, so it's just derivative on the potential function with respect to the vector field. Those are deformations generated by diffeomorphisms, and those are always inside the kernel of this operator. Okay, on condition that, of course, X should be, the vector field is 0 on the boundary, which means the diffeomorphisms are fixing the boundary. So fixing the boundary data. So we always have those non-zero kernel element, but that's, in some sense, that's okay because they are generated by diffeomorphisms. In some times, they are gauge. So we can just modulate those by choosing good gauge. Okay, so here we prove technical theorem here. It's first proved in the flat case, but then it's generalized to the more general static vacuum background case. So this theorem tells us that if the kernel space of this L only consists of those deformations generated by diffeomorphism. So if all the kernel elements are localized or in this format, okay, then we have local existence and uniqueness result. So it means that if we take any prescribed data which is near the data induced from this background metric G bar here on the boundary, then for such data we always have a static vacuum extension, and that extension is also close to the background metric G bar U bar, and it's locally unique. Okay, so based on this framework, we say that to prove this good local existence and uniqueness result, we just need to show that if we have HVs, which makes all of this equals to 0, then that HV must be of this format. Okay, so that's our aim today. So to achieve that result, we developed two approaches to do that. So let me first show you the first approach. So the first approach is to study the local existence result by this mean curvature inequality. Okay, so here let me first introduce to you this concept of static regular. So now we are considering the case where the background is the flat. So we think of G bar U bar, G as the flat metric, U bar as the constant function 1. Then let this sigma be the boundary of some Rn minus omega be the boundary of some exterior region. And we see this sigma is static regular in that exterior region if this condition is satisfied. This condition is saying that any kernel element of that linearized operator must preserve the second fundamental form. So the linearization of the second fundamental form with respect to H should be 0. Okay, so this just means that we say if HV is in the kernel, then this mean curvature linearization should be 0. So static regular is just saying that if this can be strengthened to second fundamental form linearization 0, that boundary will be called the static regular boundary. Okay, and we prove the theorem that if the boundary, if some hypersurface sigma in Rn is static regular for the exterior region, then this kernel is trivial in the sense that all those kernel elements are coming from the diffeomorphisms. Okay, and as a consequence, we will have local existence and uniqueness of static vacuum extensions nearby that boundary. Okay, and here is a rough reasoning of why this theorem is true. It's just because that if we have this HV satisfy all of that 0, then we can choose the harmonic gauge when the background is the flat. Under this harmonic gauge, this system can be simply written in this way. So interior HV are just harmonic, Laplace acting on those are 0, and on the boundary we have induced tensor from H is 0. This can be regarded as a Dirichlet data for H, that's 0. And this second fundamental form linearization is seeing that the Neumann data of H is also 0. So we see H is essentially satisfying a Laplace equation with vanishing Cauchy data. So it implies that H should be trivial. Okay, and as for the V part, we see V is harmonic. And we can actually use those two conditions on H to derive conditions of V on the boundary. And those two are actually coming from the linearization of Gauss-Kodatz equation of the boundary. Okay, so we linearize the Gauss-Kodatz equation, and we will get those two boundary conditions of V. So V is harmonic with those boundary conditions, then we can derive V is 0. Okay, so those are the rough reasoning for the theorem here. Okay, so now we say like if sigma is static regular, then that's good. We will have local existence uniqueness result. Then we will ask what which hypersurface in Rn can be static regular. So the first result I like to present is this one. We prove that if omega is a bounded open subset, so that the boundary has positive Gauss curvature. So the boundary is sigma is a convex surface in R3, then this sigma must be static regular. Okay, so and the proof of this is to use a linearized version of mean curvature inequality. So let me show you roughly the idea of proof here. So we first want to establish a linearized version of this Zhongshan inequality. Here, this is the theorem from Zhongshan, which tells us that if we have omega g, omega has positive scalar curvature, and boundary sigma has positive Gauss curvature, positive mean curvature, then this sigma can be embedded into R3. And we can compare those two curvatures as those two mean curvatures. Here is the mean curvature of sigma when it is in omega, and here is the mean curvature of sigma when it is embedded in R3. And this difference is always bigger than or equal to 0. Okay, so now if omega is already a bounded open subset in Rn, so we have sigma already a convex surface in R3. Then if we have any deformation k in the exterior region, we can compare those two mean curvatures, those two linearized mean curvatures. Okay, so the picture is, let me draw a picture here. So if we have this exterior region, this is R3 minus omega, and we have a k, which is a deformation of the metric in the exterior region, then this k will induce a deformation on the boundary sigma. So this is the sigma. Okay, which means that if we take the induced metric here, and we can perturb it by tk, induced k. Okay, so this will become a family of metrics on the sigma. And because this starting metric has positive Gauss curvature, then for small t, this also has positive Gauss curvature. Therefore, we can embed this family into R3. So it means that this k actually causes a perturbation of the embedded surface. Okay, so then for each new embedding, we will have a new mean curvature. That's embedded curvature. And so we can compute the variation of the, so I use a ring on the top here, variation of the embedded curvature which is caused by the variation of the induced metric. Okay, so we can actually just think of this part as the linearization of the first term here. Okay, and now the second one is just the usual variation of the mean curvature with respect to the deformation k. Okay, so we can compare those two, but it's not always true that this is we have some inequality for arbitrary k. We have to choose some special k here. So here I choose k to be the conformal deformation. So k is 2v times the flat metric. V is any scalar function, and we define this quantity depending on v and the embedded surface sigma. It's just this difference between the two linearization of those mean curvatures with respect to this 2vg deformation, and in extra we multiply that by 2v. Okay, and we show that actually this quantity is always non-negative if v is a harmonic function in R3 with respect to the flat metric. Okay, so this can be viewed as a linearized version of this mean curvature inequality. Okay, and once we have obtained this inequality, now we can come back to prove. Sorry.
You're linearizing around the domain of Euclidean space,
right? Yes, linearizing.
So why isn't that a minimum? Why don't you get the derivative 0 then?
Oh, okay. So let me see. So this is, so of course, if you take, if you think of this as a function from G to this, then a flat metric is the minimum. Then you just take derivative of that as 0. But that's for filling in. Like G should be the fill in of some mean curvature. Here we are actually considering extension. Yeah, so there is some important technical involving like going from this is like fill-in version to the exterior version. Yeah, so here this V is a harmonic function in the exterior region. Yes. 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 Okay, so once we have this inequality, now let's come back to show that convex surfaces are static regular. So now this is the picture. I think of the green part as exterior region, and then sigma is the convex boundary. HV satisfies the linearized Bartnik data equal to 0 on sigma. Okay, then we can take this foliation of sigma along the unit normal direction. So it's just like to take the equidistant surfaces. Then we take those two observations. Firstly, if HV is static vacuum, so if HV is in the kernel of the linearized operator, then V is harmonic. We have talked about this before. And now we can apply this inequality for the harmonic function V. So if we evaluate that quantity of V along every foliated surface, this quantity must be non-negative. Okay, so it's always non-negative. And the second observation is that actually this quantity is equal to 0 on sigma. So it achieves the minimum on sigma. It's purely because that if HV is in the kernel of L, when the background is flat, we can actually show that this new deformation, H plus 2VG, this is actually a Ricci flat deformation. Okay, so now we are in dimension 3, and it's Ricci flat, so we know that Ricci flat means flat in dimension 3. So we also develop a way to prove that any Ricci flat deformation in R3 must be flat. Okay, so this is a flat deformation. It means that this linearization of the embedded mean curvature must equal to the usual linearization of the mean curvature. Okay, and using this inequality, we can actually compute this quantity on the boundary. And because H satisfies 0 Bartnik boundary condition, we can derive that this quantity is equal to 0 when we are restricted on the boundary sigma. Okay, so now it's always non-negative. In other surfaces, it achieves minimum at the boundary, so we can take derivative, that's 0, and we compute the derivative, actually we get integral of the second fundamental form norm square. And then we derive that this term must be 0. That's the static vacuum condition. Okay, so that's the idea of proving the convex case. Okay. Okay, so now let's proceed to the next approach, which is by the perturbation method to study the local existence result near a general static vacuum background. Okay, so before I stating the main result, I'd like to just say briefly about what the difficulty when the background is static. It's a general static vacuum, not flat. So this is the equations if HV is in the kernel of the linearized boundary value problem. And we say that if the background is flat, then this Ricci term will be 0, and the U will be constant 1. So this term will also be 0, and this term will be 0. So we'll have just very simple equations on H and V. But for general static vacuum background, we have very complicated U bars. So for example, in Schwarzschild, it's not that simple already. So this will be a very complicated term, and also this, okay? And if we linearize the Gauss-Kaldasi equation, we'll also have this Ricci term won't be 0 if it's not flat, and also this one. Okay, so like for general static vacuum background, we have complicated stuff because of that U bar here. Okay, and even if we have the static regular conditions, so even if H is preserving the second fundamental form, we cannot easily prove that H is trivial. Okay, so in view of this, we introduced this new boundary condition. It's an infinite order boundary condition. Here we see a deformation HV at a general static vacuum background preserves the second fundamental form to the infinite order if those equations are true. So first one is just linearization of second fundamental form is 0. Second one is linearization of the Ricci tensor restricted on the boundary should be 0. And here is linearization of the derivative of Ricci tensor along the normal direction restricted on the boundary should be 0. And this derivative k order can be 1, 2, 3, and go on. Okay, so this is the infinite order of boundary conditions, and this is actually equivalent to the boundary condition that H preserves the second fundamental form. H should preserve the derivative of second fundamental form along the normal direction for any order. Okay, the reason we want to use this notation is just because if we write like covariant derivative of the second fundamental form along the normal direction, then we need the second fundamental form to be defined in the neighborhood of the boundary. So, but second fundamental form is defined only if you choose a hypersurface. So for this to be well defined, we need to make a choice of gauge or make a choice of hypersurfaces. That's not gauge invariant. Therefore, we use this format. This is gauge invariant. Okay. So once we introduce this condition, in an upcoming work, we are showing that this condition is true for an open and dense collection of hypersurfaces. Okay, so here is the result. We take M G bar U bar as a general asymptotically flat static vacuum triple. U bar is always positive. And we take a smooth family of embedded hypersurfaces in this background metric. This family should satisfy those conditions. Firstly, the deformation vector is always non-negative along the normal direction. Okay, so it's always deforming along one direction. Okay, and secondly, this projection factor theta is strictly bigger than 0 on some open subset. Okay, so here I'm just show you the picture here. So here we can take the smooth family to be a foliation starting from this hypersurface here. We just expand that foliation like this. This is the case where X is always positive along the normal direction everywhere. Okay, and this is another picture which we can just foliate a portion of the hypersurface. So we think of this deformation vector X as equal to 0 in those remaining part, and it has positive projection along the normal vector in this small portion. Okay, so we can take either choice. And last condition is this sigma t in this family can always be viewed as the connected boundary of some exterior region. Okay, then for this smooth family of hypersurfaces, we show that there is an open and dense subset of the time interval, so that for any time in this open and dense subset, any static vacuum deformation HV in that kernel linearized operator at that time always preserves the second fundamental form to the infinite order. Okay, so any kernel element at that time must satisfy this infinite order boundary condition. Okay, so that's the theorem here. So let me make some remarks here. So it's just saying that if a foliation like this or some perturbation like this, then we take the boundary value problem, linearize the boundary value problem at those exterior region. Okay, and for open dense choice of those surfaces, the linearization is the kernel elements always preserve this, always satisfy this infinite order condition. Okay, and if we have those further conditions on the those further topological conditions, which says that the relative first fundamental group of this sigma high t is like this small portion here. Okay, if this first fundamental group is equal to 0, and the sigma high t is the analytic portion, then we can prove the kernel of the linearized operator only consists of trivial deformations. So those deformations generated by diffeomorphisms. Okay, so we can say like if we have those conditions, then for open this choice of surfaces here or surfaces here, those are good surfaces in the sense that nearby Bartnik data can always admit a locally unique static vacuum extension. Okay, and here is the rough reasoning of why this statement is true. It's just because that we know if a pair is static vacuum, we can actually construct analytic chart for that pair. So we can construct an analytic chart near that analytic portion. Therefore, in this chart, the background metric is analytic. And if HV, a deformation, satisfies an elliptic boundary value problem, then that HV must also be analytic. And then those infinite order conditions are just essentially saying that this H actually vanished to the infinite order on the boundary. But it's analytic, so H must be trivial. Trivial in the sense that H equals to some Lie derivative on the metric. Okay, so this is true in the analytic chart near this portion sigma high t. And we show, actually, it's based on the previous work of Lan-Hsuan and Anderson. We show that if H is trivial in a small open subset, we can always show it's actually trivial everywhere on the manifold. Okay, so that's the idea of using this infinite order boundary condition. Okay, so some more remarks here. So this result tells us that if we have a hypersurface embedded in a general static vacuum background metric, then to obtain local existence and uniqueness result, we just need to perturb only a small portion of that. Okay, and also if the background metric is flat, so G bar is flat, U bar is 1, then the analytic condition can be dropped. So the surface, this portion of the surface don't need to be analytic. Okay, it's just because we have very good Laplace equation for the potential function in the flat case. And in the previous work, we also showed that using this result, in addition with a dilation argument, we can derive that any star-shaped surface in Rn is static regular. So we can find local existence or uniqueness result for any Bartnik data which is near the star-shaped Bartnik data. Okay, so lastly, this is true for general background. So it could be very nice if we can apply dilation argument with Schwarzschild background, but that's not doable. Okay, so to study further like properties of hypersurface in Schwarzschild background, we hope that we can generalize the previous approach of mean curvature comparison to get some more good results. Okay, so that's all the remarks. Do I still have some time? So lastly, let me show you the why that infinite order condition is true for open-ended choice. So here is first it's based on the variational property of the Bartnik data. So if we consider this functional, this is essentially the Einstein-Hilbert action from the spacetime, and we take first, so this functional maps arbitrary GU to this integral with extra mass term. If we take first variation of the functional, we say that HV is a deformation of GU. We say that its first variation is expressed in this way. So we say if GU is static vacuum, then this term will be 0. So this bulk integral will be 0. And if HV preserves the Bartnik data, which means if those two are 0, then this boundary term is also 0. Okay, so this means that if we consider the space of matrix with fixed Bartnik data, so this is always 0, then static vacuum matrix are critical points of this functional. And that's always the underlying reason why the remaining static matrix are candidates for critical points of ADM mass. Okay, so that's the first variation. And then we take a look at the second variation. Of course, we need to choose another deformation and vary it, the first expression here. So P is the variation of this part, Q is the variation of that part. Okay, so we know second variation is symmetric. If we switch the position of HVKW, those two should be equal. So based on symmetry of second order variation, we can actually derive this green type identity. It says that if HV is a static vacuum deformation preserving the Bartnik data, which means HV is in the kernel of the linearized boundary value problem, then for arbitrary static vacuum deformation, this pairing is always 0. So for arbitrary K, which is static vacuum, the pairing between the Bartnik data of K and those data of HV is always 0. Okay, so this is essentially telling us what's the co-kernel of the boundary map. So here, if we take a look at the boundary map, which maps any deformation KW to the Bartnik data, then this equation tells us that if HV is in the kernel of this map B, we can compute those quantities, which are from here. Those must be a co-kernel element of this map. Okay, so that's the green type identity we obtained from this functional. Okay, and now we can use this identity to prove the result we want. So here is the construction of the proof. So now we have this family of exterior regions m minus omega t. Like you can think of omega t as growing as a sphere growing larger and larger, and we have those background matrix restricting on those exterior regions. We can pull back all of them to a fixed m minus omega. Okay, so we get a family of static vacuum pairs on this fixed manifold m minus omega, and let's use this LT to denote the linearization of the boundary value problem at this background metric. Okay, so now let's suppose we have a kernel element in the kernel when t is equal to 0, and let's first suppose this is true, which means that there is a smooth family of deformations HTVT. They are kernel elements of L at t, and they are smooth with respect to t. They converge to HV when t equals to 0. Okay, which means that let's suppose this HV kernel element is actually the limit of a sequence of kernel elements nearby. Okay, then if this is true, we can just take variation of that family of kernels. So this is derivative of this HT with respect to t, and derivative of VT with respect to t, and with extra Lie derivative terms. This K and W constructed here, we can show that actually they are static vacuum deformation. So they preserve the static vacuum equations, but they are not necessarily preserving the Bartnik data. So we compute the Bartnik data of this pair. We see that the Bartnik data of this K actually is related to the variation of second fundamental form with respect to H. Okay, so this is the special element we produce. And we know that from this identity, we know that this pairing with any K here must be 0. So we just plug those back to the identity here. Okay, and do some computation. We can just derive that actually that identity tells us that this integral is equal to 0. So this theta is just the normal direction projective of the deformation vector x. okay, of the foliation vector x. So we know that if zeta is strictly positive, then in those subset, this second fundamental variation is always 0. Okay, so we get the first like Neumann condition. And then we can do induction actually. So now we observe that if A prime H is 0, we come back to here. We see this K, induced K tensor is actually 0 if this term is 0. If it's not 0, then zeta is 0. Okay, so this induced K is always 0 on sigma. Actually, this mean curvature variation is again 0 because of this equality. Okay, so with this true, we can come back and conclude that this constructed pair is actually also in the kernel. The static vacuum preserves the Bartnik data. So it's also element in the kernel of this L node. Okay, and we show any kernel in the L node must satisfy this condition. So we conclude that second fundamental form linearization with respect to K now must also be 0. And then we plug the expression of K into here, we can derive a higher order condition on H, actually. Okay, and then we do induction again. So this is true for any kernel element here, but K is a kernel element. Plug K back to here, we derive a 1 degree higher, 1 degree higher order condition for H, and we go on. Okay, so by this we can just prove the infinite order condition for H. Okay, so that's the proof part. And here, just one sentence about this assumption. We say here we suppose that HV can be approached smoothly by a family of kernel elements. Actually, this is not always true, and we show that if we have a family of elliptic operators, and we can actually choose an open this subset in that time interval t, and for in that good subset, any kernel element of that operator can be approached in the Holder norm by a sequence of kernel elements nearby, and we can also take the discrete derivative on that sequence. Okay, so to finish the proof, we can just replace the smooth derivative here by the discrete derivative. Okay, yeah, so that's all my talk. Thank you for your attention.